going to be an action or trial through which specific results are obtained. And then an outcome is going to be the result of a single trial in a probability experiment. The sample space, and we're just going to go through a few words here. The sample space is going to be the set of all possible outcomes of a probability experiment. And I'm going to give you a chance to practice some of these as well, trying to identify what's a sample space, what's an outcome, what's an event. And an event is going to consist of one or more outcomes and is a subset of the sample space. So I've got a survey consists of asking people for their blood types. There's 4 blood types. Who knows what else we need to know about these blood types? What will be the number of outcomes? What do you know about blood types?
You need to know if they're positive or negative.
Yeah, you need to know if they're positive or negative. So you've got O positive and negative, A positive and negative, B positive and negative, and so A and B positive, AB positive, negative. So let's look at our tree here. And this is what's called a tree diagram. So we've got listed the blood types first, and then we've got positive and negative. So all the possible outcomes, there's 8 possible outcomes because we've got the blood type itself and then positive or negative type as well. So that isn't an example of a sample space. All right. So a simple event consists of a single outcome. And I think that's going to be one of your questions in your homework. What is a simple event? And in this case, the example is tossing a head and rolling a 3. An event that consists of more than one outcome is not a simple event. Okay, so tossing a head and rolling an even number, that would give you pen. These, all of those. Okay. We might get through this fairly quickly because a lot of it is kind of stuff that you probably already know, but you didn't kind of associate it with statistics. So we got the fundamental counting principle. If one event can occur in M ways and another event can occur in N ways, then the events can occur in sequence M times N. And that can go for any number of events. So we've got 3 car manufacturers, 2 car sizes, and 4 colors. So given the fundamental counting principle, what should I do with these 3 manufacturers, 2 car sizes, and 4 colors? We'll go back one screen. M by N and M times N. You do multiply them. You are right. So that would give us 3 times 2 times 4, which is 24. You're right. You will multiply them. You can use a tree diagram to check your results. So let's do that. There you go. There is your tree diagram. And so off of the 4s, you have 2 compact, 2 the sizes, and then off of those, you have the colors. All right. Does that make sense? The fundamental counting principle, because we're about to take that to the next level. Awesome. Okay. So the access code for a car security system consists of 4 digits. No problem, Gabriella. Um, Each digit can be a number from 0 through 9. And we've got 3 different scenarios that we're going to look at. So the first scenario is if each digit can be used only once and not repeated. So how many digits do I have to choose from for that first digit? How many digits do I have to choose from? So we got 9 and 10 as answers, but we're talking from 0 to 9. So you start with 0 and then you count 9 after that, and that gives you 10. Right. So I have 10 to choose from. Now I can't use, I can use numbers only once. So then the second number, how many digits do I have to choose from for the second number? You're right. I only have 9. And so you see a pattern emerging. What about the third digit? How many numbers do I have to choose from? 8. You're right. And then the last one, of course, we know you got the pattern, is going to be 7 numbers. Okay. So what we're going to do is multiply 10 times 9 times 8 times 7. How many access codes are possible? What's 10 times 9 times 8 times 7? You turn on my calculator here.
5,040.
Thank you. 5,040. Perfect. Now, each digit can be repeated. What numbers are we going to multiply together if each digit can be repeated? All right. Right. So we're going to have tens on each of these because each digit can be repeated. You could have 0, 0, 0, 0. All right. And this is going to be 10 to the fourth, which is what? We'll calculator up here. 10 to the fourth power. That's going to be 10,000. Did you all get that? My chat is not moving like it's supposed to. Perfect. Thank you. All right. Last one. Each digit can be repeated, but the first digit can't be 0 or 1. So what does that mean for the first digit? What are we going to change that first digit to? If the first digit can't be a 0 or a 1, what are we going to change that first digit to? How many choices do we have? How many choices do we have to choose from? Yeah. So you guys got this pretty much down. Eight numbers you have to choose from if it can't be a 0 or 1. So then you have 10 to the third times 8. What do you get for 10 to the third times 8? All right, perfect. So we've got 8,000. And now we'll skip over to classical probability or theoretical probability. So each outcome in a sample space is equally likely. So basically, if you're talking about tossing a coin, if you toss a heads or a tails, you have 50% chance of getting either one. If you have a die, you have 1, 2, 3, 4, 5, 6 as your sample space. You toss a die. Each number is 1/6 of a chance of being rolled. So the probability of an event is going to be the number of outcomes in event E divided by the number of outcomes in the sample space. So let's do a few examples of that. Event A is rolling a 3. Rolling a 3. First of all, we have to establish what our sample space is. And in this case, if we're talking about a 6-sided die, our sample space is 1, 2, 3, 4, 5, 6. So what is the probability of rolling a 3? Well, there's only 1 3 in our sample space. So that probability, 1, is 1 out of 6. Right. What is the probability of rolling a 7? Got 1 0, 2 zeros. You're right. 0 out of 6 because we can't roll a 7, right? Because we only go to 6. What about rolling a number less than 5? No, it's out of 6, but what number would we use less than 5? Yep, 4 out of 6, because there's 4 numbers out of the 6. So you guys, this is pretty straightforward for you. I see. Awesome. No stumpers here. Well, let's skip over to empirical probability. So it's going to be based on observations obtained from probability experiments. It's going to be the relative frequency of an event. And to calculate the probability of an event, it would be the frequency of the event happening over the total frequency period. So you have F over N. And N is going to be the summation of F. Or the summation of the events. Okay. So here a company is conducting a survey of randomly selected US adults to determine how they read books during the past year, if at all. So far, 1,502 adults have been surveyed. The pie chart shows the results. Digital books include ebooks as well as audiobooks. What is the probability the next adult surveyed read only print books during the last year? What is the probability that the next adult surveyed read only print books during the last year? What will we divide here? $560 and $1,502. You are correct. So that probability is 0.373. All right. Let's see if we can stump you now. Companies conducting a survey of randomly selected individuals to determine the ages of a social media application. So far, 3,000 users of the application have been surveyed. What is the probability that the next user surveyed is 25 to 34 years old? What are we going to divide in this case? See at 546, but that is the fourth line down. We're looking for 25 to 34-year-olds. Okay, no worries. Because here is where we're looking. And you guessed it, that's going to be 765 divided by 3,000. Okay. So what do you think we would do? And I'm just skipping ahead just a little bit. What do you think we would do if we wanted to know what the probability is that the next user surveyed was not 25 to 34 years old? What would we do? How would we do different? What would we do differently there? We want to know what's not 25 to 34 years old. So I see. Okay, so Christopher gave me 2235, and then Neria told me 3,000 minus 765, which is correct. So 3,000 minus 765 over 3,000, because we're talking about everything else. And that is 2,235 divided by 3,000. Okay. Awesome. We're getting through this pretty fast. So let's hop skip over to the law of large numbers. As an experiment is repeated over and over, the empirical probability of an event approaches the theoretical or actual probability of the event. Okay. So if you notice here, the probability of tossing a head was kind of high when the number of tosses was low, right? So maybe I was getting a bunch of heads. But as I increase the number of tosses, I'm getting closer and closer to the 0.5, which is my classical probability. So you get closer and closer to that theoretical or classical probability, the more events you have as an experiment is repeated. Okay. So let's look into the types of probability. Do you have subjective probability? That is something that's like your intuition. It's an educated guess. It's going to be an estimate. Something like a doctor says you have 75% chance of catching the flu this season. Oh, here's a doctor may feel a patient has 90% chance of a full recovery. That will be an example of a subjective probability. What about this one? The probability that you will get an A on your next test is 0.9. What do you think? Do you think that's subjective? Classical or empirical? So, okay. So how do you know that you're going to make an A the next test, an A on your next test is 0.9? That is going to be subjective. Most likely you're just going to have an educated guess there. What about this one? The probability that a voter chosen at random will be younger than 35 years old is 0.3. It's 0.3. Is that classical, empirical, or subjective? Classical means it's going to be kind of in theory, and each event has an equally likely chance of being selected. Okay, got one empirical. Any agrees or disagrees with that? Yeah, got a couple of agreements with that. You're right. It is most likely based on a survey. What about this one? The probability of winning 1,000 ticket raffle with one ticket is 1 out of 1,000. Classical, empirical, or subjective? Definitely. I think process of elimination says we got to have an example of the last one. So, yeah, that is classical. There's equally likely outcomes. All right. The range of probabilities rule. So, every probability is going to be between 0 and 1, the probability of each event. 0 is going to be probably not likely to happen. 1 is most likely to happen. I'm pretty certain it's going to happen. The complement of event E, and you actually did this on a previous question, is going to be all the events that are not included in event E. So we call that and note it by E prime. The probability of the event plus the probability of its complement is going to be equal to 1. Notice if I add the circle and what's in the square, I have the entire box, which is equal to 1. So that means the probability of the event is just 1 minus the probability of its complement. And then the probability of the complement is equal to 1 minus the probability of the event. So they kind of we're just basically doing math. We're subtracting the probability of the event from 1 or the probability of the complement from 1 just to get the other value. And we already did this one. The 1 is, let's go back. So here is the probability of event is going to be between 0 and 1, like 100% in decimal. Does that make sense? The 1 is like all of it, like 100%. Okay. And we'll do a couple of examples. We already did this problem. You already figured out what the complement was. So find the probability of randomly selecting a social networking site user who is not 25 to 34 years old. And we already figured that it was 2,235 out of 3,000. Now, the way they did it here is slightly different from the way we looked at it. They figured out what is the probability of 0.255, not 0.25, of ages 25 to 34, which is 0.255. And then we subtract that probability from 1. So 1 minus the event is the probability of its complement. All right. A probability experiment consists of tossing a coin and spinning the spinner shown. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of each event. So event A is tossing a tail and spinning an odd number. Event B is tossing a head or spinning a number greater than 3. So we got to see and think about, what does our tree diagram look like? What would the tree diagram look like? So you've got numbers 1 through 8. So you toss a tail and you spin an odd number. That's event A. Let's look at the tree diagram. So A, again, is tossing a tail and spinning an odd number. So tossing a tail and spinning an odd number. So 1, 2, 3, 4. Which is then 4 out of 16, because there's 16 total elements in the sample space, and I'm only picking out 4 of them. And the 1/4 is just reducing that down to lowest form. Event B, what was event B? Let's see if we can. Tossing a head or spinning a number greater than 3. Tossing a head or spinning a number that's greater than 3. So I'll give you a few seconds. Tossing a head or spinning a number that's greater than 3. What is that going to look like? What do you think? Got 5 out of 16. Tossing a head or spinning a number greater than 3. So they said or. I see a lot of 5 out of 16s, but they're saying you toss a head or you spin a number that's greater than 3. So what we're looking at in that case is a lot more than what we originally thought. This is 10, 8, 9, 10, 11, 12, 13. Do you see what they got? So tossing a head or spinning a number that's greater than 3. So that or is what makes the difference, because I think a lot of you were thinking and. If we end the relationship, then yeah, we got to consider them both together. But since we're saying or, we got to consider both separately. And some of them actually overlap, which we'll talk about a little bit later. So it should be 13 out of 16. So toss ahead, which was all 8. And then we have to consider rolling a number that's spinning a number that's greater than 3. So there's some of those in the tails as well.
Wait, I'm confused. So when it says to toss a head, so you're including all the numbers that are tossed with the head? I don't understand that part.
Yeah, so if it says toss a head or spin a number that's greater than 3. So we're going to consider all the heads, because we've tossed, that's tossing a head, right? All those options, 8 options. And then we're going to consider under tails, what's greater than 3.
Okay, because I guess I'm making them separate. Like I'm making the numbers separate from the. I don't know what I'm doing. No, I see what you're saying.
I I get what you're saying too. You might still be on the and part, because the or is what's changing the outcome here.
Yes, ma'am.
I wonder if I have an example of this one in our text. Did I? I don't have a note on that. Oh, let's see. All right, so that was 13 out of 16. We'll check and see in our homework if we have one like that. All right, back to the codes. Back to the codes. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? So here's how I do this. 8 digits, 1, 2, 3, 4, 5, 6, 7, 8. So what is each of these lines going to represent what number? If it can be, each digit can be 0 through 9, and each digit can be repeated. What will I put on each of those lines? Right, 10. So 10, basically 10 to the 8th. And it says, what is the probability of getting your college identification number? Now, how many of those events are there? How many ways can you get your college identification number? Okay, Christopher. Just one. Just one. So one divided by 10 to the 8th. Very small. Percentage. So the longer the code, the more numbers you have, the more likely you are to have it harder to guess ID number in this case. Rest chapter 3 is actually pretty short, if you will. This presentation has only like 15 slides. So we'll get started with it, and that'll run us into our first break. So conditional probability is the probability of an event occurring given that another event has already occurred. And we denote that with P in this line, A. And we say probability of B, and this will be given that A has occurred. The probability of B, given that A has occurred. So 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. So how many cards are in a deck? Quiz, quick quiz. How many cards are in a deck of cards? $52, correct. So what happens? Let's see. Find the probability that the second card is a queen, given that the first card is a king. So if the first card is a king, how many kings are in a deck? 4. Okay. So I'm asking those questions because I've had a class once before where the students really didn't know just a deck of playing cards, how many of each thing was there. And I actually broke down, we have 4 kings, 4 queens, 4 jacks, 4 tens, 4 nines, and all the way down to 2 and 4 aces as well. And then we have the suits. We have 13 diamonds, 13 clubs, 13 hearts, 13 spades as well. But if we need to break that down any further, if we have any more of these questions, then we'll break it down. +2 jokers. Thank you. +2 jokers. All right. So we want to know the first card is a king and it's not replaced. So there's a king. There's 4 out of 52. Because the first card is a king and is not replaced, the remaining deck has 51 cards. 4 of those are going to be queens because the only thing you pulled from was kings. So that probability is 4 out of 51. So the probability that the second card is a queen, given that the first card is a king, is going to be 4 out of 51. Does everybody see where that number comes from? 4 out of 51. Okay. Because we're gonna try another one. All right. The table shows the results of survey in which 970 U.S. adults were asked whether they have ever ridden as a passenger in a self-driving vehicle. Find the probability that an adult is 18 to 64 years old, given that the adult has ridden as a passenger in a self-driving vehicle. So the probability the person is 18 to 64 years old, given that they have ridden, I'm going to put yes, they have ridden in a self-driving vehicle. What do you think that probability is? So you're looking at, given that they have driven or have ridden as a passenger, so your denominator, right, Neria, that's right. Your denominator is going to be 225. And your numerator would be 202. That's an easy mistake to make because we've been using the entire set the whole time that we've been kind of talking about this. So 202 divided by 225. Okay. All right. So now let's look at independent versus dependent event. Um, it's independent if the occurrence of one event does not affect the probability of the occurrence of the other event. So that means the probability of B given A is just going to be the probability of B because A doesn't matter. The probability of A given B is just going to be the probability of A because the probability of B doesn't matter. And then again, events that are not independent or dependent. So let's decide whether these events are independent or dependent. Number 1, selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. Are these events dependent or independent? I got a lot of dependents. This is dependent because the first one depends on the second one. Because you took out a king, so that left 51 cards. So one is dependent on the other. What about this one? Tossing a coin and getting a head, and then rolling a 6-sided die and obtaining a 6. And this A and B on the screen are like, this is event A and this is event B. All right, we got lots of independence. Okay, good. I'm glad it makes sense. This is going to be independent because it doesn't matter what if I toss a coin, that's going to be independent from rolling the die because they're two separate objects that I'm taking the probability of. All right. Okay. Driving over 85 miles per hour and then getting in a car accident. Independent or dependent? This one is a little morbid. What do we think? Well, I tend to agree with you that it's dependent because you're more likely uh, to get into an accident if you are going above 85 miles an hour. All right. Let's see if we got one more of these. All right. We're going to start with the multiplication rule when we come back from multiplication rule. So the probability that two events A and B will occur in sequence is the probability of A times the probability of B given that A has occurred. The probability of A and B is the probability of A times the probability of B given that A has occurred. And so I think they're going to give us, and if you're got independence of events, it's going to be the probability of A times the probability of B. And that can be extended for any number of independent events, just like when we saw the fundamental counting principle, how we could just multiply, multiply, multiply. Well, we can do the same thing with probability with independent events. All right, two cards are selected without replacement. Or do they say replacement? Without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. Well, let's do this again. A king, so is going to be 4 out of 52. And what about a queen? If you've taken one card out of the deck and you're not replacing it, what's my next probability? 4 out of 51. Right. So that becomes our multiplication. So this is the probability of B given that A has occurred. And the probability of A is selecting a king. Yeah, they are dependent events. Okay. Let's see. And that is 16 divided by 2,652. What about this one? A coin is tossed and a die is rolled. A coin is tossed and a die is rolled. What's the first probability? What's the probability of tossing a coin, getting ahead? Okay, so we got half. And then rolling a 6. What's the probability of rolling a 6? Okay, so these are independent or dependent events. They're independent. So we're looking at that one, the probability of A times the probability of B. So that's half times 1 over 6, which gives us 1 over 12. And on these questions, usually they'll want you to enter in the fraction, so you can leave the fraction there. If they ask you for a decimal, pay attention to how many decimal places that you're going to go out. Okay. Wow. Going through this one kind of fast. Okay. So for an anterior cruciate ligament, I did not know that was what ACL stood for. Now we know. reconstructive surgery, the probability that the surgery is successful is 0.95. Find the probability that 3 ACL surgeries are successful. Okay, so are we talking about independent or dependent? Does one surgery depend on another surgery? Got a lot of independence. That means since they're independent and they occur in sequence, then the probability is going to be 0.95 times 0.95 times 0.95. That's 0.95 cubed, right? I think it's not working. What's 0.95 cubed while I get my AirPlay working again?
Point 857.
0.857?
Yes, ma'am.
Okay. Confirmed. 0.857. Thank you. Okay. So this AirPlay actually doesn't stay on. That's not fun. Um, but it looks like we're gonna have time to get to 9.1 where we're gonna need it. All right. Next, find the probability that none of the 3 ACL surgeries are successful. What will we be multiplying together in this case? None of them are successful. Yep. For one not to be successful, it will be 0.05. So we're calculating if all 3 of them are not successful. So what are we multiplying together?
Wait, can you remind us where the 0.5 comes from? I mean, 0.05?
So successful is as 0.95, right? So the complement of that is 1 minus 0.95.
Oh,
So that
okay.
would be 0.05. So now, okay, good. So now we're talking about 3 of surgeries that are not successful. So we're going to multiply this 0.05 3 times. Oh, wow. So it's a very small likelihood that all 3 of them are going to be unsuccessful. And you hate to be that doctor or hate to be that doctor's patient. Surgeries is successful. Hence, we're going to use the answer that we got prior to now, the one that we just got here, 0.000125. So the probability that at least one is successful. Well, This is going to be 1 minus the probability that none are successful. Let that sink in. When I was doing statistics, this one caught me up. The probability of at least one success is equal to 1 minus the probability that none were successful. So basically what they're saying is it's not none, it's at least one. So we will subtract away the probability that none of them are successful. So that's that 1 minus 0.000125. Was it 3 zeros? Yeah. And so that is 0.999875. The probability that at least two are successful. Okay. So, wow, that's the right screen. Mutually exclusive events. We're talking about the addition rule. Two events A and B cannot occur at the same time if they're mutually exclusive. Let me get a graphic up here. These two events on the left are mutually exclusive. They don't have any outcomes in common. You have not mutually exclusive events if they have events in common. Outcomes in common, excuse me. All right. We're going to determine whether these events are mutually exclusive. Explain your reasoning. Event A is rolling a 3 on a die. Event B is rolling a 4 on a die. Is this mutually exclusive, meaning they can occur at the same time? Or is this not mutually exclusive? What do you think? Right? You can't roll both at the same time. So what about this one? Randomly select a male student, randomly select a nursing major. Yeah, both could be true at the same time. You could have a male that's a nursing major. All right. What about you randomly select a blood donor with type O blood and you randomly select a female blood donor? Mutually exclusive or not mutually exclusive? Got some knots. Couple of knots. We got some agreements there. Yep. The female she can have an O blood type. All right. So then we jump into the addition rule. And so we had to define what's mutually exclusive, what's not, so that we can process the addition rule. The probability that events A or B will occur is the probability of A plus the probability of B minus the intersection of A and B. And that's what this is, probability of A and B. If you got mutually exclusive events, A doesn't depend on B, they don't overlap. They don't have any outcomes in common. So if they don't overlap, we take out that piece of overlap, that P and A and B, probability of A and B, and we're just left with probability of A plus probability of B. Okay. And we can extend that to any number of mutually exclusive events. All right, let's try it. You select a card from a standard deck. Find the probability that the card is a 4 or an ace. A 4 or an ace. Are they mutually exclusive or no? Okay, I got a not and I have a is. So find the probability that the card is a 4 or an ace. But do they have any outcomes in common? The fours and aces. There's 4 aces in the deck, but the fours and the aces have anything in common. If I laid out all the fours and I laid out all the aces, do they have anything in common? They are mutually exclusive. So then that means I'm just adding their probabilities together. So yeah, it would be 4 out of 52 twice added together. Right. Both of them have a probability of 4 out of 52. Okay. You roll a die because you can't have fours. Fours don't overlap aces. And the question was, why is it mutually exclusive? Because fours don't overlap aces. If I said something like aces and spades, well, they have one overlapping, right? Because there's one ace that is a spade. But in this case, we don't have any overlap. Does that make sense? So an overlap might be if I have spades. So if my first one is spades and the second one is aces. Well, there's 4 aces in a deck, but one of those aces is a spade. So they would overlap. Does that make sense? So one ace is a spade. In this case, there is no overlap because the fours can't be aces. Does that make sense? Right. A 4 is not an ace. And they don't have any overlap in that case. Cool. All right. What about this? You find the probability of rolling a number that's less than 3 or rolling an odd number on a die. So my sample space for the die is 1, 2, 3, 4, 5, 6. What is the probability of rolling a number less than 3? Say X is less than 3. What is that equal to? Right. 2 out of 6 is a number that's less than 3. And the probability of rolling an odd number, what is that? 3 out of 6. Is there any overlap? Here's numbers less than 3, and here are odd numbers. There is. So in that case, we're going to add together 2 out of 6 plus 3 out of 6, and then we're going to subtract out the overlap, which is 1 out of 6. So I think someone guessed it earlier that it was 4 out of 6 as the answer. Which would be correct. Does everybody see how we got 4 out of 6 here? This 1 out of 6 is where we overlap. Didn't hear from a couple of people. I was just looking to see if they were going to weigh in. The probability, just to recap, we have an overlap here. So we had the probability that X is less than 3, the number is less than 3, so that's 1 and 2. And then we had the probability that there's an odd number, so that's 1, 3, and 5. Well, 1 appears twice, right? So there is an overlap on these two events. Okay, so in that case, I add the two probabilities together, 2 out of 6 and 3 out of 6, and subtract away the overlap, which gives me 4 out of 6. Okay. Hooray. Let's get a picture here.
Wait, Professor, go
Uh-huh.
back. Explain that last part again, where you say you weighed in on the 1 out of 6 that got the 4 out of 6.
Right. So this 1 out of 6 is where we overlap. We overlap just 1 out of 6 outcomes. So see here,
Okay.
does that make sense? Because 3 is odd. Yeah, 3 is odd. So 1, 3, and 5 are odd. So that's how we got 3 out of 6.
Okay.
The overlap is on 1. No, the overlap might not always be 1. So why not 3? Why not 3 what? Like, why isn't 3 where the overlap is, or?
Yeah, I'm sorry. So you said so the number less than 3 is an odd number, so you wouldn't count 3 as odd because it's less than 3? Like, is 3 part of that equation as well, or like would
Oh,
the
okay.
overlap? Yeah.
For the first part, it's just 1 and 2. And
Okay,
then for the
3 is
second
not.
part, right, it's
Okay.
not in it.
Okay. Thank you.
Mhm. Right. Let's look at the picture. Here's the picture. So odd is 1, 3, and 5, and then less than 3 was just 1 and 2, so the overlap is 1. All right. I think we got it. All right, here we got a frequency distribution. We got enough of those last week, didn't we? You probably remember a number of them from your homework. The number of months in which a sales representative reached each sales level during the past 3 years is what is given here, the volume of sales and the number of months. Using the sales pattern, find the probability that the sales representative will sell between 75,000 and 124,999 next month. Well, I'll give you like a second to kind of think about it. And then we'll get into what the answer is. Okay, so between 75,000 and 99,999, there was 7 months. But we move into the next bracket for event B. These two are mutually exclusive. So we're just going to add them together. How many did I have all together? Months. 15, 16. Which is 36 altogether. But that's 16. Yeah. Doesn't that look like 36 to me? 8 plus 6, 15, 16. 6. That's 36. That's 36. All right. So we're just going to add them together because they're mutually exclusive. Oh, all right. So blood bank catalogs the types of blood, including whether you're Rh positive or Rh negative, given by the donors during the last 5 days. Find the probability that the donor has type O or type A blood. Type O or type A blood. Are these events mutually exclusive or not mutually exclusive? Type O or type A blood? Exclusive or no? Okay. Okay. You're right. They are mutually exclusive. So that means we're going to add up their probabilities separately. So we would have 184 divided by 409 plus 164 divided by 409. Because the two are exclusive. You can't be O and A at the same time. Does that make sense how we did that? Okay. Find the probability the donor has type B or is Rh negative. So Christopher, put that together for us. What did you add and subtract?
I added together the 184 and 164 donors who had type O and A blood before dividing it by the total of 409 donors to get 0.85085, which approximates to 0.8509, which when put into percentages is 85.09%.
Okay, perfect. I thought you were on this one, the Rh negative, and I was like, wait, that was fast. You were giving us the exact for this one here that we were just working on. Yeah, I was thinking, wow, he's super fast. What about this one? Are we mutually exclusive or no? We are not. We are not. So, what are we adding and subtracting? What are we adding and subtracting here? So, type B, 45 over 409, and then RH negative, 65 over 409. And then we're adding those two. What are we going to subtract away? Yep. It's going to be the 8 over 409, the overlap of 8. Right. Right. So there's a little bit of overlap. So we did good with adding the two together. And then, but we just had to get rid of the overlap. Okay. And I think that ends. Recap, a summary of the probability that we looked at so far. If you want to take a screenshot or take a quick picture, you can. This is probably going to be in your PowerPoint as well, though. One where we're going to be using the computer, the calculators, and I'm going to be showing you some things in StatCrunch and showing you some things in Words, the TI-84. There you go. I know I had some words. Okay. So we start with permutations. So this is called additional topics in probability. And a permutation is going to be an ordered arrangement of objects. So the number of different permutations of n distinct objects is n factorial. N factorial. Factorial is that exclamation mark. So let's do some examples. 0 factorial is always going to be 1. And if I had something like 6 factorial, that means I'm going to multiply every integer below 6 along with 6. So 6, 5, 4, 3, 2, 1. Multiply all those together and get 720. And then 4 factorial, multiply those together and you get 24. So, do you all recall seeing factorial before, or is this kind of new? Okay. Okay. Lots of news and some remembers. Let's apply. All right, the objective of a 9x9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3x3 grid contains the digits 1 to 9. Anybody remember playing Sudoku? It became popular for a minute there. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? How many different ways? Well, Oh, your daughter is smart. Avery, how'd you get that number? 362,880. How'd you get that? Multiply each number from 9 to 1. Okay. Well, you would be correct. You would be correct. And let's look at the two different ways that we can put this into our technology. And we'll start with the TI 84 Plus because some people said that they are using this. So where we're going to be for these problems is in the math menu. So you'll click on math, math, and you'll go over to PRB. Once you're at PRB, you see that the exclamation mark there, factorial. Now, it's pulling in the answer that I just had before it because I didn't put in the 9 first. So let me clear that out. And I'll put the 9 in first, and then math, PRB, and then that exclamation mark, which is factorial. So that's how we do it there. Now, let's go to StatCrunch because some of us will be using StatCrunch. Now, you can get to StatCrunch from within a problem. So if you're working on the homework, just go to the help and you can pull up StatCrunch from there. But it's data, compute, expression, build, and it wants us to use the word fact. Sort for factorial, put the number in the parentheses, and then okay. And then compute. That is strange. That is strange to me too. Because what is the exclamation mark there for if I can't use it? But anyway, that's how you do it in StatCrunch. So use the word fact. And that's going to be the first thing we learn how to do. Now, what about the permutation of n objects taken r at a time? Now, this is a little bit different. And there's a formula to it. But there's also a way to do it in your calculator and in StatCrunch. So here's our formula. It's n factorial divided by n minus r factorial. All right, so here's a question. Find the number of ways of forming 4-digit codes in which no digit is repeated. Well, 4-digit codes, 0 to 9, that's 10 digits. So n is 10. And 4 at a time is r. So here's the notation that we use. Ten objects taken 4 at a time. We can't be repeated. Order matters. With permutations, order does matter. And so when they say when no digit is repeated, that clues you in that this is a permutation. So notice they have that P up there. Well, let's look and see. On the calculator, okay, same menu, math, Oh, math, PRB. You see this NPR on number 2? Now, I know this is hard to see, but there's a little small box, a big P, and a small box. So that's where I'm going to put the 10. And the other spot is where I'm going to put the 4. And I get 5,040. So math, PRB, in the NPR. Math, PRB, NPR. And then you fill in the 2 numbers. In StatCrunch, we have words again. Can I just go to this options edit? Let me go through the whole thing again, just in case, so we remember how to get there. Data, compute, expression, build. I wonder if I can clear these out. No, it won't let me do that. Perm, for permutation. Look for perm, and it's going to pop up parentheses with a comma in the middle. So N is going to be the first number you enter, and R is going to be the second number you enter. So perm for permutation, 10 and 4. So okay, and compute. So notice it puts it in this other column for me. Okay. All right, each year, 33 race cars start the Indianapolis 500. How many ways can the cars finish first, second, and third? What are our 2 numbers? What is N and R in this case? I think that was under data. Yeah, data, then compute, expression. So N would be 33, and R is 3. I see some 500s there. The Indianapolis 500 is the name of the race. About that. So we're going to do 33, and 3. So however you are accessing technology, either you're using a TI-84 or you're using a StatCrunch, you've got both ways here. So you don't have to necessarily go through and do the factorials there like that, but you can. If you should so choose, you can. Okay. Distinguishable permutations. So the number of distinguishable permutations of N objects where N1 are of one type, N2 are of another type, and so on. N3 is of another type, and 4 is of a different type. Looks like so. So you have N factorial over N1 factorial times N2 factorial. It probably doesn't make a whole lot of sense right now. When I put it with an example, you'll see what I mean. So in this case, a building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. So altogether, that's 6 plus 4 plus 2, which is 12. So you would have 12 factorial on the top. And in how many distinguishable ways can the houses be arranged? 12 houses in the subdivision. You got N1, N2, N3. and 6, 4, and 2. And so here's the setup. We've got 12 factorial or n factorial over 6 factorial times 4 factorial times 2 factorial. Sometimes we see this with letters. Let me see if I have another example. Nope, they don't have another example for these. But the premise is you take the whole of the group as your numerator in factorial, and then you break down each piece for the denominator. And they're giving you the TI-84 plus steps. So that would be 12 math prob factorial divided by, I always use parentheses, 6. It felt like that factorial was somewhere for 2. There you go. Okay. So we did permutations. Permutations are where order matters. Combinations, on the other hand, are a selection of R objects from a group of N objects, and that's without regard to order. You don't have to have them in order. Here's this formula. It's N factorial divided by N minus R factorial times R factorial. Now, the difference between permutations and combinations is right here in this R factorial. That's what we're adding on. All right. A state Department of Transportation plans to develop a new section of interstate highway and receive 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? Now, in this case, order does not matter. You're selecting 4 companies from the group of 16. So N equals 16 and R equals 4. Order is not important. And so that way, that means we're going to use a combination. So same kind of steps, same place. Let's go to the calculator first. Same pace, math, PRB. This time it's NCR number 3. And what were the numbers? 16 and 4, 16 and 4. I keep wanting to hit it with my mouse, but it's airplaying from my phone. So that's why it looks like I'm pausing here, but it's just because I'm like effectively translating between my phone and the computer. So there's 1,820 different combinations there. So StatCrunch oh, my little window's in the way. Data, compute, expression, build. This time it's comb for combination, COMB. 16 and 4. And that's 1,820, 1,820. Okay. Got a summary. Again, this is y'all's study slides. So this is definitely in your resources for you. Let's find probabilities. And that's a little more involved. So let's just kind of look and see how we're going to solve for the probabilities. All right. A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What is the probability of randomly selecting the 3 members who will be chosen for the board? Okay. 1 out of 4,080. So there's 4,080 possibles, but because there's only one favorable outcome, the probability of selecting those 3 members is 1 out of 480. Right, for those particular positions. And the only reason we don't use Excel is because when you're taking the test, I want you to be able to use what you're going to be able to use for the test. So like you can use the calculator for the test. You can use StatCrunch on the test, but you can't open up another window, which would be Excel. Okay. All right. Find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. Okay. So we need to do a bit of background here. So in a standard deck of playing cards, 13 cards are diamonds. It does not matter what order the cards are selected. The possible number of ways of choosing 5 diamonds out of 13 is 13 combined with or in combination with 5. There are 52 cards in the deck. And if you choose 5 at a time, you get this big number, the 2,598,960 number. But because for the diamonds, there's only 13 and you're choosing 5 of them, that's what becomes your numerator for this probability. Is there another one? Oh, there's another one. Does this make sense? I'm just going to pause right there because the probabilities when you're using combinations can be tricky. Okay, we'll try another one and see. So a food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. 4 kernels are randomly selected from the sample. What is the probability that exactly 1 kernel contains a dangerously high level of the toxin? All right, so the possible number of ways of choosing 1 toxic kernel out of 3 toxic kernels is 3 in combination with 1, which is 3. The possible number of ways of choosing 3 non-toxic kernels from 397 non-toxic kernels is given here as the 10 million. Is it the letters, the C and the P?
It's the whole thing for me. I don't know, just the numbers next to the letters. I'm just a visual person. I think it's just kind of throwing me off. I don't know. I'm just trying to listen.
Okay. We'll finish this one out. So then, is this it? We haven't even gotten to the probability part yet. Using the multiplication rule, the number of ways of choosing 1 toxic kernel and 3 non-toxic kernels is given here. This is the 31,049,370. Now, we need to figure out the total. So of 400 kernels, 4 are chosen. So now the probability of selecting exactly one toxic kernel is going to be what we had before, the 31 million, divided by, let's go like 1 billion, 1,050,739,900. So these problems, if you notice, this 400 is equaling this 397 and 3. When you have problems kind of like in this format, these numbers are going to add up together. 3 and 1 is 4. And I noticed that in your homework on question 18, we'll follow this premise. Question 18. Times 918. Is this the last one? Let's go keep that. Let's go look at question 18. And 3.4. All right. You are dealt a hand. Document. Let's make this bigger so we can see. Whoa, too big. All right. You are dealt a hand of 8 cards from a standard deck of 52 cards. Find the probability of being dealt 5 clubs and 3 cards with 1 card of each other remaining suit. What I did with the Word document. Now, in total, you've got 52 and you're choosing 8 cards. So this is my denominator. Oops. 52 in combination with 8. That's my denominator. But then they said, find the probability of being dealt 5 clubs. Well, there's 13 total clubs in the deck, and I'm choosing 5 of them. Then it says you want 3 cards with 1 card of each other remaining suit. So 13 combination with 5, and then the remaining suits, 1, 2, 3. That's the setup. So here is probability of being dealt 5 clubs. And these are 3 cards with 1 card of each of the remaining suits. 1, 2, 3 cards. Notice 5, 6, 7, 8 is here. And then 13, 13, 13, 13 is 52. And you would put that in your calculator. Okay. Let me see if there's any more I want to look at before we move forward to something else. All right. In a certain lottery, you must correctly select 4 numbers in any order out of 33 to win. You purchase 1 lottery ticket. What is the probability that you will win? Okay. Where's my Word document? Come back. In any order. So this is a combination. So 33, choose 4. What's the probability that you will win? There's only one winning number. So 1 divided by 33 in combination with 4. Okay. So these are going to take some doing. Again, get more help. View an example. Help me solve this are all ways that you can get help. You can always ask me. StatCrunch is here. You don't have to go through the way we went through to get to StatCrunch. I went through the main screen. But that is 3.4 done. And 18 is probably the hardest one that you will do. And you have the blueprint for 18 in this lecture. Okay. Let's get rid of that. Now, we're not finished. We hop skip over to chapter 9 from here. And we start talking about correlation. So I'm just going to get us started with correlation, and hopefully I can kind of show you the StatCrunch steps that you'll take. And the StatCrunch steps for 9.1 will help you with 9.2 as well. Okay. What is correlation anyway? It's going to be a relationship between 2 variables. There's going to be an independent variable, which is normally X, or we call it the explanatory variable, the variable that explains what's happening. And Y is going to be the dependent variable for response. So in a scatter plot, the order pairs X, Y are graphed as points in a coordinate plane. You probably remember what a scatter plot looks like. The independent variable is measured on the x-axis, and the dependent is measured on the y-axis. Here are some scatter plots. When they say negative linear correlation, that means you're close to forming a line. As x increases, y tends to decrease. That's a negative linear correlation. Positive linear correlation is when we're moving up from left to right. As x increases, y tends to increase as well. So from left to right, I'm moving up. No correlation at all, points are all over the place. That's no correlation. And then we also have a nonlinear correlation. And that looks like here, this looks like a quadratic, right? Or a parabola. So that's nonlinear. Now, they're giving us some points here. And one is the gross domestic product, and the second one is carbon dioxide emissions. So the gross domestic product is going to be X, carbon dioxide emissions is going to be Y. And we've got the scatter plot. There appears to be a positive linear correlation. Why? Because when I move from left to right, I am increasing. I'm moving up. All right. A student conducts a study to determine whether there is a linear relationship between the number of hours a student exercises each week and the student's grade point average. Interesting. The data are shown in the table below. Display the data in a scatter plot and describe the type of correlation. So here's our scatter plot. It appears there's no linear correlation between the variables. Yeah, because the points are all over the place. I was trying to find one that would give us like a small number so we can put it in the calculator. But let's this thing does this. Let's look at how we put this in the calculator. And then we'll look at StatCrunch, and that might be our time. Back on the calculator here. All right. Figure out a place to put this. So what you have to do is go stat, edit. Now I've got some information in my list one. So what I did was I went up to L1 and I pressed clear, then enter. That gets rid of the whole column. I'm gonna do that on all of these just so we don't have stuff cluttering the way. So I've got my list one, and I'm just gonna put in the values 3, 0, 6, 10, 2, 18, 14, 15, 5. That's my list one. Then I'm going to go to list two, 3.6, 4, 3.9, 2.5, 2.4. And in this section, 7, 3, it's advantageous for you to use StatCrunch so you don't have to enter in all the numbers, but I've got them in. I need a scatter plot. I went, second stat plot is not going to get it to you. Graph is what I went to. So once you get the list one and list two, graph. Okay. Now, when you're working with StatCrunch and when you get these problems in your homework, let's go to it. I want to, instead of typing all those numbers in again, I want to find a question. We can look at 9.1. Okay. Looks like we click here to view the data table. And so age and vocabulary size, you go to this double window and then open in StatCrunch. That's why I was saying that it's advantageous to use StatCrunch on these particular problems because it will pull in the data for you from the question. And so we go to, I can do a scatter plot here, but stat, regression, simple linear. I'm going to kill two birds with one stone because this is what you're going to use for 9.2 as well. You'll select X as your age and Y as your vocabulary size. And then you don't need to select anything else. You can click on compute. It's going to give you a bunch of information here. But what we want right now is our scatter plot. And so you'll right arrow over and you'll get your scatter plot here. So let's go back to the question itself. It says display the data in a scatter plot. Choose the correct graph below. Well, we know it's not going to be A or B because the Y was the vocabulary size and it was measured from 0 to 3,000, it looks like. Yep, looks like C. If you want to, in StatCrunch, like this goes from 0 to 2,500. Again, you can click on that hamburger. Oh, I went to x-axis. I meant to go to y-axis. Hamburger, and go to y-axis, and then go from 0 to 3,000. And then you get something that even better matches what you see on the answer choices. Okay, we'll leave that there. So that's how you do the calculator, TI-84, and StatCrunch to find the scatter plot. Okay, now the correlation coefficient. How well or what is the strength between these two variables? That's the correlation coefficient. That's what it tells us. The symbol R represents this number. Notice there's a fancy Dan Doodle equation for us to calculate R. We are not going to calculate R in that way. We are going to get it from technology. And you'll notice in your homework, it's going to say use technology to find R. Okay, the population correlation coefficient is represented by what looks like a P, a lowercase p, and we call that rho. The range of the correlation coefficient is from -1 to 1. Negative correlations go from -1 to about 0. 0 means we have no correlation at all. -1 means I have a perfect negative correlation. It's a perfect line. So see, if R is equal to -1, there's a perfect negative correlation. That means it falls in a straight line, all your dots. If R is close to 0, points are all over the place. And we saw an example of that earlier. And then if R is equal to 1, all the way over on the other end of the spectrum, there's a perfect positive correlation, meaning that my points form a line, a straight line, perfectly linear. So let's look at some correlations here. R equals 1, we know it's a perfect straight line. Well, what about R equals 0.81? Notice I'm still forming this line structure. It's still pretty linear. It's a strong correlation. It's strong and positive, but it's not 1. It's 0.81. Notice 0.45. You're getting closer to 0, right? You're getting closer to 0. So my points are becoming a little more scattered. I can still tell that I'm increasing from left to right, but again, I'm getting close to 0. So my points are kind of a little farther off from what a perfect correlation would be. Down here at the bottom, I'm looking at negative correlation. So a perfect negative correlation, again, your points form a line and decrease from left to right. A strong negative correlation, I can still kind of see the linearity of the relationship, but my points aren't all on one line. And then the last one, no correlation at all. That means points are everywhere. There's no, we can't distinguish a pattern. So let's look at our StatCrunch results. This is why I took you to linear, simple linear, regression, simple linear, because the correlation coefficient is here. It's 0.975. So that's pretty strong. Notice I look like I'm pretty much in a straight line. Just a side note, in 9.2, you will be asked for the equation of the line, and that's here. Now, I haven't put the equation of a line in the TI-84 in a while. So what I'll do is I'll post in the class how to do that. Because I think I have a TI-84 cheat sheet that I'll post in the class. So you can see all those functions. And if I need to, I'll make a video. Okay. I just don't remember off the top of my head how to do it in the TI-84 right at the moment. Okay. Got a strong correlation there. And we're going to calculate the correlation coefficient for this gross domestic product and the carbon dioxide emissions data. What can you conclude? All right. We get 0.874 is positive. So as the gross domestic product increases, so does the carbon dioxide emissions. And then it's asking me to use a technology tool again, but the problem with that is, okay, we need this part. The problem with that is that we have to enter all the data in. So we're not going to do that right now. Again, if you use StatCrunch, you can pull that data in from just the problem itself. Here, we're talking about testing a population correlation coefficient. We're going to use table 11 in Appendix B to find our critical R value, our critical value. And then we're going to test it with our correlation coefficient. So if R is greater than the critical value, there is enough evidence to decide that the correlation coefficient is significant. Let's look at what that looks like. So we want to determine whether rho is significant for 5 pairs of data, n equals 5, at a level of significance of alpha equals 0.01. Well, this is table 11. This is alpha equals 0.01, so I'm looking in the second column. My n, 5 pairs of data, is 5, and so I'm looking at this 0.959. So I will compare that to R. Let me see if it's here. If R, the correlation coefficient is greater than 0.959, the correlation is significant. Otherwise, there's not enough evidence to conclude that the correlation is significant. And I believe that, let me go back to the screen, that a number of your problems in your homework use this. Let's see. Here we go. Let's do an example. So we've got our Old Faithful data. They gave that to us. We're going to now see, is the correlation coefficient significant? We're going to use alpha equals 0.05. Okay, so we get our table, and the table is going to be in your problem. It'll just ask you, it'll say critical value table at the top in the problem section. Alpha equals 0.05, n was equal to 25, so we come down to 25. And if R is greater than this number, then the correlation is significant. Remember, our R was 0.979, which is greater than 0.396. which means the population correlation is significant. And then there is enough evidence at the 5% level of significance to conclude that there is a significant linear correlation between the duration of Old Faithful's eruptions and the time between eruptions. Correlation does not mean causation. Just because they're correlated doesn't mean that one caused the other. And I wanted to look at, in our last few minutes, one of the problems that you'll come across. Okay. So on that same problem we were on just a few minutes ago, we decided that C was our answer. And did we get the correlation? We did. It was 0.9752665, but they want us to round to 3 decimal places. That's why I just copied the whole number. 3 decimal places would put me at 0.975. Check my answer. Describe the type of correlation. There is what type of correlation is this? We have a few. 0.975. Weak negative, perfect positive, strong positive, perfect negative, strong negative, no, or a weak plus. The 3, 4 people, 5. Strong positive. Good job. Okay, interpret the correlation. What was this between ages and words in their vocabulary? I'll let you read through the choices and let me know which one, A, B, C, D, E, or F, is true. Got 1 A so far. Okay. Got A, so we'll go with A. Okay. All right, so use a table of critical values for the Pearson correlation coefficient to make a conclusion about the correlation coefficient. Let alpha equals 0.01. So here's where you'll click on this table. There's 11 children, so I'll come down here to n equals 11, and I'm at 0.735. That is my critical value. So if R is greater than my critical value, then the correlation is significant. So the critical value is 0.735. Therefore, there is or is not sufficient evidence. What do you think? Is there sufficient evidence? There is sufficient evidence that there is now. Wouldn't say there's no correlation. There is sufficient evidence at the 1% level to conclude that there is a significant linear correlation between children's ages and the number of words in their vocabulary. Pretty good. All right. I believe that if you could get through that example, understanding each piece as we went through, I believe the rest of these are the same. You're going to have to do and follow the same process. 10 through 13. And then 14, you're going to have to compare correlation coefficients. So, excuse me, you'll find the first one and then you'll delete out. Let's see, a 12th data point was added to the end of the data set for a child who is 6 years old and it has this vocabulary. So you won't delete, you'll be adding another data point to your data and then finding the new correlation coefficient.